All right, so we're going to conclude sections 13.5 and 13.6 in this video, and we're going to work on one, maybe two more problems. So first we're going to start on page 861, and we're going to look at number 17, which is actually one of you all suggested problems, but I'm just going to point out some different things in this problem that relate to topics we've discussed. So a particle travels along the parabolic path y equals x squared from left to right, where x and y are in meters. The temperature at any point xy in the plane is given in degrees Celsius by T of xy equals 40 over the quantity 1 plus x squared plus y squared. All right, so let's just first start with that, and then we'll get into the question. So let's just sketch a little picture of what we have. So we have the parabola y equals x squared, and it says we're traveling from left to right. So it's y equals x squared. And then they give us a temperature function. They ask us, what is the rate of change of the temperature experienced by the particle as it travels along the parabola at the moment the particle passes through the point -2, 4? Hint, find an appropriate directional derivative. So given the hint that they gave us, let's just kind of establish what we need to do. So first off, for a directional derivative, we need a point, of course, and they gave us a point, but we also need a unit vector that points in the direction of travel, or the direction in which we want to find the rate of change. So we wish to find a unit vector that points in the direction of travel of a particle moving along y equals x squared at -2, 4. All right, so there are a couple of different ways that we can go about finding this. Now, you all know how to parameterize this and do it that way. I'm also going to reference an equation from you all's reading, so I'll do this two different ways, finding the vector that we're looking for, this unit vector that we're looking for. So first, we're just going to find a vector that points in that direction, then we'll divide by its magnitude to make it a unit vector. So I'll do this two different ways. So you can use, let's see, a rationale similar to that of equation 1 on page 838. And if we look at it that way, then we have, given that y equals x squared, the derivative of y with respect to x is equal to 2x. And you can look at this as like the change in y over the change in x. So this would be 2x over 1. But when I first introduced partial derivatives, I discussed them in this same fashion, where gives you the slope of the tangent line when you take the partial derivative. So you can do this that same way. So in the direction of travel, tangent vector. Because we have a vector to work with here. This is change in y over change in x. So your x is 1, because this is 2x over 1. And your y would be 2x. So that was the same way that I explained that when we were talking about the partial derivatives. And now we're just using an ordinary derivative here and doing the exact same thing. Now, another way that might be more intuitive, or that you may be more accustomed to, so it may be more intuitive if we just took this thing and we parametrized it and then had an r of t, and then we just take r prime of t. Either one of those works, and they're going to give you the exact same thing. So to parameterize y equals x squared as you can do r of x or r of t. So I'll do r of t just because that's what we normally do. So r of t, but it doesn't matter. You can use whatever you want to. We could use x. R of t equals t comma t squared. So remember, you have a function of one variable. You can make this independent variable t, and then y would just be equal to t squared. So x would be equal to t, y would be equal to t squared. Then we see the tangent vector is r prime of t, which equals 1 comma 2t. So same thing we got there. Doesn't matter which way we do it. I'm just using different variables. It doesn't matter which variables you use either. So now that we have our tangent vector, we need to look at that tangent vector at the point that they gave us, which was -2, 4. So now the reason I did this both ways is largely because I wanted to point out the equation 1 on page 838, because it's an important pair of equations. There's actually two equations on there, but they give you the tangent vector for any surface. So it's good to know those, or actually for curves, it's good to know those two equations that are on page 838, or equation 1 on page 838. All right, so now we need the tangent vector at our point x equals -2 or t equals -2, whichever way you want to look at it. So at x equals -2, we have, so this is going to give us a vector that points in the direction of travel at that particular point. So the direction vector, before it's a unit vector for directional derivative problems, we normally call it a. So that's why I'm calling it a here. This is not an a for acceleration. It's just that a, or actually let's just call it r prime of t, r prime of -2, so that we don't think it is acceleration. So r prime of -2, which equals 1 comma -4. All right, so now we have our direction vector, but we need it to be a unit vector in order to use the directional to talk about the directional derivative. So the length of this, so the length of 1 -4 is equal to the square root of 17. So our unit vector is going to be 1 over the square root of 17 comma -4 over the square root of 17. So now we have this unit vector, and now we can, now what we're going to do is take the function that they gave us, t of xy, which I haven't written down on here yet. We're going to take its partial derivatives or its gradient, the gradient vector, whichever way you want to look at it. We take the gradient vector and dot it with this, or take f sub x and t sub x multiplied by this and t sub y multiplied by that. All right, so now the function that they gave us was t of xy equals 40 divided by 1 plus x squared plus y squared. So we need the partial of this with respect to x and the partial of this with respect to y. So t sub x equals, we're going to get, if we were to bring this up to the numerator and we're taking with respect to x, we'll get negative quantity 1 plus x squared plus y squared to the negative 2. And then times the derivative of the inside with respect to x is 2x, and then times our 40. So negative 40 times 2x over this raised to the second power 1 plus x squared plus y squared squared. And our t sub y is going to be identical with the exception of that's going to be a y. So t sub y equals negative 40 times 2y over the quantity 1 plus x squared plus y squared quantity squared. All right, so now we're going to put in our point, which was negative 2, 4. And we're going to take this and multiply it by that. Put in our point negative 2, 4 here as well and multiply it by that. And that will give us our directional derivative. All right, so d sub u, not ft, sorry. D sub u of t of xy equals, so we're going to get here, we'll get negative 80x and then times 1 and then minus 80y times 4. So this is going to be negative 80x and then that was times 1 and then plus, what did I say, negative 80y times 4 times negative 4, excuse me. So that's going to be plus 320y all over 1 plus x squared plus y squared quantity squared. So how did I get that? Just so we can go back and see how I came up with that. So I did this t sub x times u sub 1 plus t sub y times u sub 2. So I'll just write that over here as well. This was t sub x times u sub 1 plus t sub y times u sub 2. And that's how we got this. And now we just need to plug in our point, which was negative 2, 4. So we get, when we put in negative 2, we get positive 160. And then plus, we're putting in 4, what was that, 1280 over, we are putting in negative 2 there, which gives us a 4. And we put in 4 there, which gives us 16. So we get 21 squared. Oh, you know what? I lost something. from my one of my U2, I lost their denominator. So let me fix that. So this should have a square root of 17 in the denominator. I made the unit vector and then I didn't use it. I used the vector that wasn't a unit vector. So I need that to make sure I have the unit vector. Yeah, that's the only thing is negative. All right, so now that's square root of 17 times, this was 4, 16, 21 squared, whatever that is. And that's what we would get there. All right, now that was just part A of the problem. Part B of the problem says, suppose the particle travels at a speed of 5 meters per second. How fast is the temperature changing with respect to time as the particle passes through the point -2, 4? All right, so I actually won't have time to finish part B here. So let's see, what do we get here? So this is in degrees Celsius per, let me look at the units on what we have here. Degrees Celsius per meter. Per meter. So degrees Celsius per meter. And now part B, suppose the particle travels at a speed of 5 meters per second. 5 meters per second. How fast is the temperature changing with respect to time as the particle passes through the point? This, okay. So we're going to take what they gave us, and they told us that the speed is 5 meters per second. So, and our end result, how fast is the temperature changing with respect to time? So we should end up with degrees Celsius per second here. And we're still at that same point, and we started with the unit vector here. So because we have that unit vector in this directional derivative, now we're just taking this speed and we're going to take that into account. So we're going to take this and multiply it by what we have here, 160 plus, I guess I could simplify that, but too late, I already wrote it. The square root of 17 times 21 squared, and this is degrees Celsius per meter, which those cancel, and we get whatever that is, 5 times 160 plus 1280 over the square root of 17 times 21 squared degrees Celsius per second. That's what we get for part B. All right, so that concludes sections 13.5 and 13.6, and we'll start 13.7 in our next video.